Magnetic chains on superconductors, a major leap toward quantum computing. In the race to build the next generation of quantum technologies, the fusion of magnetism and superconductivity holds enormous promise. A new breakthrough may have just brought us one step closer to that future. Researchers at Songshan Lake Materials Laboratory have developed a hybrid material system that successfully engineers atomic-scale magnetic chains on a superconducting surface, a feat that could play a vital role in the development of topological quantum computing. The key lies in the interface between magnetism and superconductivity. In theory, when these two distinct quantum states coexist under the right conditions, they can produce topological superconductivity, a rare and exotic state of matter that can host quasiparticles known as Majorana modes. These elusive modes are not just scientific curiosities. They are considered ideal building blocks for fault-tolerant quantum computers due to their resistance to local disturbances. But turning theory into reality has proven extremely difficult. Traditional systems attempting to integrate magnetic and superconducting materials often face a series of obstacles. Lattice mismatches between the two materials can introduce disorder, making it hard to detect or sustain topological states. Interfaces are also prone to complex interactions that can either obscure the signs of true topological behavior or, worse, mimic them with more trivial effects that are not useful for quantum computing. Moreover, controlling magnetic structures down to the atomic level has remained a formidable challenge, until now. In a recent study published in Materials Futures, the team introduced a new heterostructure composed of a sub-monolayer of chromium telluride, CrTe₂, deposited on a niobium diselenide, NbSe₂, substrate. This approach is remarkable not just for its materials but for the precision and control it achieves. By carefully depositing both chromium, Cr, and tellurium, Te, atoms onto the NbSe₂ surface, the researchers documented a two-stage growth process that lays the foundation for controlled magnetic behavior. Initially, a compressed CrTe layer forms, featuring a lattice constant of 0.35 nanometers. This early stage of growth sets the groundwork for the second phase, the development of a highly ordered, atomically flat CrTe₂ monolayer with a slightly expanded lattice constant of 0.39 nanometers. But the real breakthrough comes during the annealing process. When the initial CrTe layer is thermally treated, it undergoes stress relief reconstruction. This reconstruction doesn't just smooth out the surface, it creates a distinctive stripe-like pattern with edges that host localized magnetic moments. These edges form what can effectively be considered one-dimensional magnetic chains, an essential feature for engineering topological states. Using scanning tunneling spectroscopy, or STS, the researchers confirmed the existence of these magnetic moments. More importantly, they observed Yu-Shiba-Rusinov, YSR, states located precisely at the edges of these stripe patterns. These YSR states are direct evidence of interactions between magnetic atoms and the underlying superconducting substrate, and they represent a signature of localized bound states, a crucial requirement for any platform aiming to host Majorana modes. What makes this heterostructure particularly promising is its tunability. The stress-induced patterns can be modified through careful control of strain, offering an unprecedented level of manipulation at the atomic scale. This opens the door to engineering customizable magnetic chains, potentially fine-tuned for specific quantum behaviors. It's not just about building a new material, it's about building a platform that can be optimized, adapted, and scaled for future quantum devices. Looking ahead, the research team plans to expand on this foundation by refining their control over strain through advanced annealing techniques, substrate modifications, and dynamic modulation strategies. Each of these approaches could allow even greater precision in aligning magnetic chains with superconducting properties, bringing us closer to detecting genuine topological superconductivity. To validate and extend their findings, the researchers also aim to carry out large-scale statistical studies and advanced spin-resolved measurements. These efforts will be essential for unraveling the complex interplay between strain, magnetism, and superconductivity in this engineered system. The goal is to move beyond isolated observations and toward a deeper, reproducible understanding of how these physical phenomena interact in real-world applications. This achievement marks a major milestone in the search for practical quantum technology. By leveraging inherent lattice mismatches to craft one-dimensional magnetic structures, the CrTe₂/NbSe₂ heterostructure offers a powerful new materials platform. It could serve as a cornerstone for both quantum spintronics and topological quantum computing, where information is stored and processed using the spin of electrons and topologically protected states, respectively. The ability to tailor magnetic properties at the nanoscale, especially when combined with the robust superconductivity of NbSe₂, may enable new classes of quantum devices that are both scalable and resilient. As quantum science progresses, strain-engineered materials like this could form the building blocks of a future where quantum computing is not just a theoretical concept, but a practical and transformative reality. This research doesn't just advance the field, it redefines what is possible at the interface of magnetism and superconductivity. In doing so, it opens entirely new avenues for designing materials that are purpose-built for the quantum age.